Hi guys, welcome back. So in this episode, we're going to talk about von Neumann and Morgenstern axiomatization. These two fellows are sort of the fathers of game theory, and so their contribution is very, very important for economic theory and or for economics and also in finance. So they basically start an axiomatization for expected utility theory. Remember, our purpose is can we rationalize this expected utility behavior, and under what circumstances? Is like what should be the preference of an individual satisfy so that we can represent his utility function with an expected utility function. So the first, so we are going to talk about two axioms, all right? Two axioms. We can actually talk about, a bunch of others, but I'm going to focus on two. One of them is called independence axiom, independence, and the other one is continuity. We're not going to spend too much time on continuity because it's sort of a technical assumption we need. The independence is more intuitive one. But anyway, for any one of, so for both these axioms, we need a sort of a definition about how we add two lotteries, okay? So I have a lottery P and then I have lottery Q. All right, so I want to find a weighted average of this lottery. So how can I do that? Meaning, let's say, so these are two lotteries over some finite set Z, and I have alpha, which is a number between 0 and 1, and I want to say something like alpha P plus 1 minus alpha Q. All right, I'm going to put this circle around plus because it's not real plus, all right, because I am adding two lotteries. So how is this defined? Well, we have to define this mathematical object. And then second, what is the intuition behind this? So let me talk about the intuition part first. The intuition, well, we call this compound lottery, by the way. And the intuition is the following. Well, this is sort of a two-stage lottery. Well, first, P or Q realized, all right? Meaning there's a draw, a random draw. So the outcome is going to be either P, the lottery P, or the lottery Q. With what probabilities? So P is going to occur with alpha probability, and Q is going to occur with 1 minus alpha probability respectively. Okay? As simple as this. And then what? Well, once we learn which lottery will be selected, and then if it is P, well, the outcome Z will be realized according to lottery selected in stage 1. Okay? So if it is, for example, P that's realized in the first stage, well, then in the second stage, we're going to get outcome Z with probability P of Z, okay? And if Q is selected or realized, so here it's not really a selection, right? It's a random event. So with alpha probability, P will be realized. So we call it, we use the verb noun realization. So it's not a choice, really. And then Q will be realized with 1 minus alpha probability. So if Q is realized, well, then in the second stage, we're going to, the Z will be selected or the realized with probability Q of Z. All right, so this is what compound lottery is. But mathematically, again, how do we define this? Well, simple. You can always think P and Q as vectors, right? Which is what I keep doing in my examples, like P1, P2, all the way up to Pm. So let's suppose the number of number of outcomes in Z is M. All right, so this is probability of outcome 1, probability of outcome 2, probability of outcome M. All right, and Q is basically Q1, Q2, all the way up to Qm. So you can think of lotteries as vectors. And so this is nothing but multiplying a vector with a scalar. So this is a real number between 0 and 1, like 1/2, 1/3, 1/4. So you basically do a scalar multiplication. So alpha p is basically this, alpha times p1, comma, alpha times p2, comma, all the way alpha times pn. All right, so what is 1 minus alpha times q then? Well, 1 minus alpha times q1, 1 minus alpha times q2, all the way up to 1 minus alpha times qn. And so how do you add two vectors? Well, you do addition component-wise. So for that reason, it's important that all the lotteries are coming from the LZ, meaning they all have m dimension. And so it's basically alpha times p1 plus 1 minus alpha times q1, the first component. I'm going to skip the second component. And this is m, by the way. I'm sorry, not n, because I used m there, so it should be m. Sorry for my confusion. And so here it's alpha pm plus 1 minus alpha qm. All right. So this is basically what the compound lottery alpha p plus 1 minus alpha q is equal to. All right. Very good. So once I have this definition, this idea of compound lottery, then next is the independence axiom. All right, so here's how it goes. Independence, I'm going to call it I. So for any P, Q, R in LZ. So for any three alternatives, for any three lotteries, and for any alpha in between 0, 1, closed, open interval, it really actually doesn't matter whether it's open or closed, but let's leave it this way. P is at least as good as Q. All right, so this is how you should read it. A preference relation satisfies independence axiom if for any P, Q, R, a lottery, and for any scalar alpha in between 0 and 1, P is at least as good as Q if and only if, equivalent to saying that alpha P plus 1 minus alpha R is at least as good as alpha Q plus 1 minus alpha R. Okay, that's it. By the way, this is, so if you think of this at least as good as like greater than or equal to, and if you think this P, R, Q like real numbers, integers or reals, so it basically says the following. Look, if a real number P is greater than or equal to Q, when I multiply both sides with alpha, and if alpha is a positive number, it shouldn't change this the sign of the inequality. And if I add the same number, positive or negative doesn't matter, will also not change the sign of the inequality. So it's very, very similar in that sense. All right. So the independence. So I am calculating a compound lottery in incorporating P and R versus Q and R. All right. So basically, I am looking at a weighted average of these two lotteries, PR and QR. Well, if you are thinking P is at least as good as Q, well, you should be still thinking that this compound lottery is at least as good as this one. It actually makes a lot of sense, right? I mean, look, to me, it's like P is better than and Q. All right. So now I'm generating a compound lottery, like two-stage lottery. Either P will be realized or R. Here, either Q will be realized or R. But you know what? In either case, if R is realized, right? I mean, it's R in both sides. But if P is realized here and Q is realized there, well, clearly P is better than Q for me. So therefore, this compound lottery should be at least as good as this compound lottery, right? It makes sort of, once you understand it, it makes perfect sense. But of course, it's a very strong assumption anyway, because it says your preference relation should satisfy this if and only if condition, and for every P, Q, and R, where PQ satisfies this, obviously. So for any R and for any alpha. All right. So here, although it sounds or looks like sort of intuitive, one thing that I should underline is that here, once you incorporate this or introduce this compound lottery, actually here, you know what? R can be realized, and here Q can be realized. Well, yes, the probabilities are sort of symmetric in both cases. But I am actually adding additional uncertainty here, right? So if you are a type of guy who doesn't like, for example, sort of the dispersion and or, I don't know, it's like the minimum, some preferences actually do not satisfy this, okay? Because this R can actually disturb your preference relation, because it may bring additional uncertainty. I mean, additional uncertainty means what? I am leaving it vague at this moment. But yeah, this is what independence axiom is, okay? So next, continuity. Okay, so a preference relation satisfies continuity axiom if P is, well, this is a strictly better than Q, which is strictly better than R, all right? So it's not at least as, because I don't have this, so it's strictly better than. That means, by the way, I mean, if P is strictly better than Q, that means P is at least as good as Q, and it's not the case that Q at least as good as P. Okay, this is how we define strictly preferred to. All right, so indifference is not going to happen. I am definitely not indifferent, so I can't say greater than or equal to. All right, so they're never equal. You're never indifferent. You strictly prefer it. Okay, so if P is strictly better than Q, and we read it as strictly better than, or strictly preferred to. If P is strictly preferred to Q and Q is strictly preferred to R for some PQR, then there exists alpha in between 0, 1, so this alpha guy, such that Q is indifferent to alpha times P plus 1 minus alpha times R. And once again, there's a circle around this plus because this is a compound lottery. I think I forgot to put this circle around plus when I gave you the definition of independence. If so, I am sorry. But yes, it is sort of a special sum, right? So be careful about it. Okay, by the way, for those who don't know what indifference is, well, an alternative is indifferent to Q means that P is at least as good as Q and Q is at least as good as P. This is how we define indifference. All right? So, therefore, continuity basically means the following. If I prefer the P guy over Q and Q guy over R, I can find some weighted average of P and R, like the best and the worst, among these three lotteries. I can find a compound lottery or weighted average of P and R such that my Q is indifferent to that guy. Okay, so there is such alpha. So this is what continuity is. What does it bring? We need it technically, for technical reasons, I mean, without continuity assumption, if you remember Dobrow's theorem, theorem. So if you remember, if you have a preference relation preference relation, which means what? A binary relation which is complete, transitive, and reflexive. If you don't remember them, please go and check the math reviews. So a preference relation is a binary relation that is complete, transitive, and reflexive. So we know that if a binary relation is a preference relation over a set of finite alternatives, well, then there exists a utility function which represents the preference relation. So what does represents mean? So a function u represents this preference relation means that if for any two alternatives A is at least as good as B, is equivalent to saying utility of A is greater than or equal to utility of B, right? So that's what a function represents, a preference relation. So if there is such a function, then we say this is a utility function. Remember all that? If you don't remember all that, well, we talk about all this in the advanced micro theory course. So maybe you should go and check those videos. So the problem was occurring when the set of alternatives was not finite. So let's say it's an infinite number of alternatives, which is the case in LZ, right? Even though Z is a finite set, LZ has an infinitely many lotteries because it's a simplex. So all lotteries are allowed. Well, over an infinite set, however, a preference relation may not have a utility representation. And lexicographic preferences is just one example for this. So for the existence of a utility function, we need a continuity. And so if you remember the de Bro's theorem, he says, if there exists if the preference relation is continuous over LZ, well, then there exists a utility function which represents this preference relation. All right. So therefore, again, if my preferences satisfies continuity, well, then I can always find some utility function which is going to represent my preference relation. What does that mean? That means if my guy, the decision maker, has this preference relation which satisfies continuity, I don't really need to know his preference relation. All I need to know his utility function. So the utility function is going to behave exactly the same as the preference relation. But there is a nice theorem by von Neumann and Morgenstern, and they basically say the following: if the preference relation is continuous and satisfies the independence axiom, two things, well, then we have a utility function. But further than this, von Neumann-Morgenstern theorem says the exact form of this utility function. So let me just write their theorem more formally. And for the rest of our course, especially in game theory, we are going to keep using expected utility theory again and again and again, because that's the way to calculate utilities in all those environments. So theorem von Neumann-Morgenstern, it basically says following: let this binary relation be a preference relation on LZ, satisfying the independence axiom and C, continuity axiom. All right? Again, I refers to independence axiom that I mentioned. C refers to continuity assumption axiom. There are numbers V of Z for each outcome. All right? So once again, if the decision maker has a preference relation, a complete transitive and reflexive binary relation over lotteries, which satisfies the independence axiom, right? And the continuity axiom, well then there will be numbers that this decision maker is attaching to each outcome, like winning 1,000, winning $10, and 0. Some numbers, such that when he calculates lottery P and, when he compares lottery P and Q, he is in fact comparing their expected utilities. So we call this expected utility of lottery P, which is equal to summation for overall outcomes, P of Z times V of Z. We have seen this utility representation, utility function, remember? Greater than or equal to the expected utility of Q, which is equal to, again, summation over all outcomes, Q of Z, V of Z. So we call V of Z as, that's it, that's the theorem. Bernoulli numbers or von Neumann Morgenstern numbers. Okay? Yep, that's it. So once again, if the decision maker has some preference relation over lotteries, all right, over this set, there are infinitely many alternatives in this set. But this preference relation is not only, this binary relation is a preference relation, meaning it's a complete transitive reflexive, but also it satisfies independence, additional assumption, and it satisfies continuity that we just defined. Well, then this theorem says, well, for this decision maker, each outcome has some value, V of Z. All right? So V of Z basically ranks the alternative over outcome set. So if it is $1,000, $10, $0, so these each outcomes, you can rank them according to V. If the lottery is giving the outcomes something like a BMW, a movie ticket, and then grocery shopping, well then your V function ranks them. So this is your V function. But when it comes to ranking the lotteries, right, like winning a movie ticket and grocery shopping is equally likely, and the other outcome is zero probability. This is one lottery. The other lottery is that you're going to win BMW or the car first with probability 1, and the other outcomes are going to happen with zero probability. So this is another lottery. So when it comes to ranking lotteries, you're going to use this U, the capital U function, which we call expected utility. How you calculate this expected utility, so the von Neumann-Morgenstern theorem gives you the structure. The De Morgan's theorem doesn't give you this structure, but with additional assumptions, independence and continuity, independence, von Neumann gives you the structure. It says, well, the decision maker will care not only about the values, but also about the probabilities. All right, so his preferences are not degenerate. It's like, you're not going to be looking at dispersion, or you're not going to be looking at only the minimum outcomes value. So you're going to evaluate both the probabilities, the distribution, and the values according to this finite sum. And so whichever lottery gives you higher expected utility, all right, you're going to pick that lottery, or you're going to rank that lottery above the other. All right. Basically, that's it about expected utility theory. And yep, and that's it for today.